Okay, so I'm actually sitting here in a cafe and drinking coffee and having a cookie and doing the screencast for you guys. And you can see that today's, what we're going to be doing is doing stoichiometry problems where you start with a solution. Now, let me crunch my cookie for a moment there. Don't forget, crew, that when you're dealing with a solution, let's imagine here we have a beaker. And in that beaker, we have a particular solution. It's going to be inevitably an aqueous solution. And if the compound is dissolved in this aqueous solution, then it's going to be homogeneously spread out throughout the solution, like so. But what's important to understand is that this solution was created when I put in a certain amount of compound into the water. So imagine here's a scoop, and I have inside that scoop a whole bunch of this compound, and then I tip it into this thing, stir it around, right? And I'm left with the solution that is the homogeneous solution. But what's critical for you to understand here is that I could mass out this amount of compound that I have in the scoop beforehand. And that's not going to be different. That's not going to change if I put this into 2 liters of water versus putting it into 100 milliliters of water. It's going to change the concentration, but it's not going to change the amount that I originally put in to that amount of water. So that's a very important thing to consider here. Let's imagine I take for 2.6 grams of sodium chloride, and I put that into, in this case, 1 liter. And then I do the same thing. I take another 2.6 grams of sodium chloride, and I put that instead into, well, I should make this a little bit bigger. I put this into 2 liters of water. Despite the fact that we understand that vessel A is going to be twice as concentrated as vessel B, in terms of the amount of sodium chloride that I actually put into each of the vessels, that's not different. And if we have the number of grams of sodium chloride, I can actually very easily convert that to the number of moles of sodium chloride. You guys all know how to do this. I have to get the molar mass for chlorine, the molar mass for sodium. That would be the number of grams. What is it? I should look this up. Hold on. Okay, so there you have it. I have 1 mole of sodium chloride would be 58.443 grams of sodium chloride. So I would take my 2.6 grams of sodium chloride. I know that I want to end up with moles of sodium chloride. 58.443 grams sodium chloride. Crank that out, and you can see that I end up with 0.0445 moles of sodium chloride. Now, that's important because don't forget molarity is the number of moles per liter. So that means I have a 0.0445 molar solution in this case, but it would be exactly half of that in the case of my B, or 0.0222, well, 4 for my molarity of my B solution. So I have 2 very different concentrations of solution, but I started off by putting in the same number of moles of compound into this. That's going to be an important thing to understand as we move forward to do these kinds of problems. So let's take a look at one such problem. Now, this type of problem that I'm going to address here is pretty complex because it's going to be a limiting reactant problem, just like the ones that you guys have dealt with the past couple of days. But I'm going to include then the concept of molarity and coming from a solution standpoint. So let's put together this question so you can see what it's about. Okay, so here's the question. How many liters of hydrogen gas can be made, if assuming we're at STP, if you start with 275 milliliters of a 6.3 molar solution of HCl and 23 grams of magnesium? And I show the reaction. It's not balanced, but I show the reaction. This is a reaction that we've actually done in lab before, so it shouldn't be completely unfamiliar. Now, I'm sure that when you look at this question initially, you probably have no sense of where to begin. And And of course, as I've always told you, you really want to start off with determining the number of moles of something. But moles of what? Well, it doesn't really make a difference where we start. We're just going to go, in this case, let's start with the solution. So there's the solution. How do we get the number of moles of HCl if this is what we have for our solution to begin with? It's actually a pretty simple thing once you understand what you need to do. Don't forget that 6.3 molar means the same thing as 6.3 moles of hydrochloric acid per liter of solution, per 1 liter of solution. But we don't have a full liter, we only have a portion of a liter. In fact, we have 0.275 liters, because don't forget that you need to make sure you divide this by, that 1,000 milliliters is equal to 1 liter. So I'm going to then multiply this by this equivalency by 0.275 liters, and that's going to give you the number of moles of hydrochloric acid I have in that amount of solution. And that equals 1.7325 moles of hydrochloric acid. Okay, so we're in good shape here. We want to make sure that we circle this dude up right here so we don't forget this piece of information. But we're going to hold on to that for just a moment. I'm going to move to the next page so I can get some more room here. Actually, before I do, I want to make sure that we remember that we have 23 grams of magnesium, so we also need to figure out the number of moles that represent 23 grams of magnesium. And you can see here I've set this up. You probably knew we were going to be doing something like this. But I take my 23 grams of magnesium. My equivalency that I created from looking at the periodic table is 1 mole of magnesium per 24.305 grams of magnesium. And when I pound this into my calculator, I get 0.8663 moles of Mg. Okay, and again, I'm going to square this up. We don't want to forget that, because those are going to be important for us to do the next piece, which is a limiting reactant piece. Oops, I just realized that that was the wrong number. I put it into my calculator wrong, just like you guys do. It's actually 0.94, thought it looked a little odd, 0.9463 moles of magnesium. Okay, so now we need to make sure that we approach this as a limiting reactions problem. And I'm going to go back to our original reaction here, and we want to know how much hydrogen gas is created. So that's going to be the thing that I focus in on in terms of my product, right? Now, if this is not a balanced equation, we need to go in here and change things around so we can make this a balanced equation. And you can pause it if you would like, otherwise you can just see that I'm going to balance this equation in a moment. And to do that, I'm going to put a 2 in front of my HCl here, and that's all I need to do, all right? So I need to have 2 moles of HCl for every 1 mole of magnesium to make 1 mole of H2 gas. Okay, let's scooch back over to where we are here and see where this is going to take us. Okay, sorry for the skip there. So now you could say I set this up because I need to make sure that I take into account mole ratios, and so I know from my balanced equation that there should be 1 mole of H2 gas to every 2 moles of HCl. I know that I have 1.7325 moles of HCl, so let's go ahead and calculate that. And that's going to give me 0.8663 moles of hydrogen gas would be produced in that situation. And let's go ahead and do the same thing, but this time we're going to imagine that we have an unlimited amount of hydrochloric acid, and we have 0.9463 moles of magnesium. And for this, we have to make sure that when we go back and look at this, the equation, we see there's an assumed 1 associated with my magnesium, and assumed 1 associated with my hydrochloric acid, so that when we jump over here, we'd have a mole ratio of 1 mole to 1 mole. And when we put this into the calculator, I think you can figure it out without even using a calculator. Surprise, surprise. It's going to be the same value. So 0.9463 moles of H2 gas here. So, looking at these two things, which one is going to be the limiting reactant? Remember, it's always the one that is going to produce the smallest amount of the product that you're going for. And in this case, clearly, this is going to be our limiting reactant, or I should say, that's going to be the amount that's produced with our particular limiting reactant. So that is our HCl. Okay? So don't forget that the problem's not over, because I asked you to tell me how many liters of hydrogen gas are produced if this is happening at STP. And I think at this point you guys know how to do these problems. They're pretty simple. We are going to use our 22.4 liter thing to equivalency in order to solve this problem. And when we go ahead and do this, we can see that our equivalency is 22.4 liters over 1 mole, and we're just going to use the 0.863 moles of 663 moles of hydrogen gas, and boom, we get 19.4 liters of hydrogen. So let's go back to our original problem just so we know what we're taking here. It said how many liters of hydrogen gas can be made at STP if you start with 275 mils of a 6.3 molar solution of HCl and 23 grams of magnesium. All right, so there you have it. Wasn't that fun and easy? Probably not, but I think once you get some practice doing these things, you'll see that they're actually not too bad as long as you've understood how to do other stoichiometry problems up to this point. Okay, goodbye.